this time we combine two kinds of portals. One having a portal with the Higgs sector and the other with photons. And we also found a rich phenomenology there. So I will tell you about what is the parameter space where the dark matter is possible in that scenario, and then detection opportunities at colliders. And then I will summarize. Okay, so probably I don't need to convince you that much that there is some mysterious thing in the universe that makes up more than 25% of the energy of the universe today. That is in presence of something that has some gravitational interactions, but we have no idea about the nature of this substance that we call dark matter. We know that the role of this fluid is to support matter in dark matter halos, and it plays a fundamental role in the formation of structures around matter radiation equality, because we know that if we only consider baryons as the constituents of the large structure in the universe doesn't have enough time to form these large structures that we observe today. So we know that the structure formation should have happened earlier than the baryons decoupled from the CMB. And this means that we need that this dark matter is not made of baryonic stuff, but instead is something new. So what we know is that if it's at all coupled via other couplings that are not gravitational, they should be really weak. And therefore, this dark matter component has to be weakly coupled to the standard model, has to be quite abundant in the universe in order to account for all this energy, and has to be long-lived such that it's present until today. And in order not to interfere with this structure formation, it should be non-relativistic, which means, or we usually say that therefore that it's cold. Now, I want to motivate the introduction of portals to the hidden sector. So, so far we have not detected dark matter in spite of all the experimental efforts in many directions, right? Looking for heavy mass candidates and also lightweight candidates. And this maybe implies that the sector where this dark matter resides, this hidden sector, is secluded in a way that maybe dark matter only interacts to our visible sector via mediators. And this is actually a quite compelling idea that's been gaining a lot of strength in the community, such that we should open one or several portals to access into this hidden sector. And there is the well-known Higgs portal that therefore couples extra scalars to the Higgs sector. We can have a vector portal, which is also known as the kinetic mixing, or neutrino portal, or the axion portal that I include here because it's quite important for what I'm going to tell you. And of course, we should also keep minimal in the sense that we do not want to have so many free parameters that in the end we lose predictability. And this is what I want to show you today, that even if we consider a more complex hidden sector with more than one candidate for a dark particle, even though in that situation we can have a rich phenomenology and we can have we can make predictions and we can test these models in the laboratory as well. Okay, so the way I'm going to motivate the dark matter production is via freeze-in. which I remind you, it's like a decussing or the so-called freeze-out mechanism. So in the freeze-in, we assume that initially the dark particles have zero initial abundance, and this abundance is built from the plasma, from interactions, from processes that produce dark matter from the thermal bath. And the particle in the end never reaches thermal equilibrium because the interactions are still quite weak, such that in the way of reaching this thermal equilibrium, the particle eventually just freezes in and freezes its abundance in a value that is expected, that it matches the correct relic abundance of the dark matter observed today. This freezing is highly dependent on the nature of the couplings. And in this sense, contrary to what happens with freeze out, you get a higher relic abundance in freezing for higher couplings or for higher cross sections, which is the opposite for the freeze out production mechanism. So in simple terms, when you consider your Boltzmann equation to find the abundance of your dark matter candidate, you neglect the initial abundance of the particles, and basically you assume that all of them are produced from the thermal bath. So we can have two distinctive freezing processes, as I said, depending on the couplings of your dark matter particle. So, for instance, if you are thinking about renormalizable couplings, for instance, this scalar dark matter model that I'm showing here, such that the masses of the particles involved are much smaller than the reheating temperature. And for reheating temperature, I mean, I will be more precise later, but I mean loosely that is the highest temperature in the universe, at highest temperature attained in the universe in the past. So basically you find what I just said, that the relic abundance of this particle is directly related to the coupling strength like this. But if you have a non-renormalizable coupling, for effective couplings of dimension 5 or higher, this is not the case anymore. And the yield of the dark matter abundance, actually depends on the scale that suppresses the coupling. In this case, I call this scale lambda. So the yield goes as 1 over lambda squared and is directly proportional to this reheating temperature. Of course, in here, I'm assuming that this lambda is the highest scale in the effective field theory. So we end up with two types of freezing processes depending on, as I said, the nature of your field theory. So for this infrared freezing or the standard freezing, you have this slow rise of the abundance of the dark matter until it freezes in this value. But if you have this UV freeze in via these non-renormalizable couplings, because this is really dependent on the highest temperature in the universe, then you have this abrupt and fast rise of the abundance, and the particle really quickly freezes into this constant value. Okay, so freezing is this really nice idea for dark matter production that even though it secludes dark matter, this is the price to pay, because usually in order for the particle not to thermalize in the early universe, it requires really small couplings. Oops, sorry, I don't know why it goes so fast. Yeah, so now I'm going to tell you a bit about what I mean by this reheating temperature that will play a quite central role in the results I will show you. So our most accepted picture of the evolution of the universe is that the universe first went through this cosmic inflationary era at some really unknown in principle energy scale that, according to observations from the CMB from Planck, it could be as high as 10 to the 14 GeV. And this would be, roughly speaking, the energy scale of inflation, which for our terms, it will be actually the temperature of this reheating, or this end of the cosmic inflationary period. On the other hand, we know that the earliest window we have to our primitive universe is through the primordial abundances of light elements, this Big Bang nucleosynthesis, which tells us that the universe had to be radiation dominated at about the scale of the mega electron volt. So in principle, what we do in the cosmological standard model, lambda CDM, is to assume that after this inflationary era, after the reheating phase of the universe is basically radiation dominated, all down to the matter radiation equality, so of the order of the electron volt scale. And this is quite strong assumption, right? Because basically we are going from a period of around 10 to the 14 GeV to the mega electron volt scale, assuming that the universe is radiation dominated, which in principle doesn't need to be the case. In what it follows, I will motivate that maybe the inflationary period ended not at some really high energy like 10 to the 14 GeV, but it could have ended anywhere between these two scales, as far as we do not interfere with Big Bang nucleosynthesis. So in simple terms, what I'm trying to say is that this reheating temperature has this lower bound, that it has to be, sorry, that in here it should be, has to be bigger. This is wrong in here. Has to be bigger than this 4 mega electron volt scale in order not to interfere with Big Bang nucleosynthesis. So this is where opportunities for detection in freeze-in dark matter appear, because in principle, if the dark matter mass is below this reheating temperature, its abundance is Boltzmann suppressed. It's not hard to convince that this is the case, because when you have a reaction that creates the dark matter for any two standard model particles annihilating into a dark matter pair, for instance. But if this particle has a mass that is higher than the temperature in the plasma, then in principle, the reaction is not possible, because these standard model particles do not have enough energy to create the dark matter pair. But since, of course, actually the energy in this plasma is a distribution, so only the particles that are in the Boltzmann tail, in the tail of the Boltzmann distribution, have enough energy to make this process happening. That's why the process is quite suppressed, but still possible to happen. And when you then compute your relic abundance of a process like this, you find that because of this Boltzmann suppression, in order to compensate that to reach the dark matter abundance, the observed dark matter abundance, now the coupling of this dark matter with the standard model is your old coupling, but corrected with this Boltzmann suppression, which is an exponential of the mass of the dark matter particle divided this reheating temperature. So actually your coupling can be much, much, much higher because of to try to compensate this Boltzmann suppression. So dark matter production is forced to happen at a stronger coupling. And this is one of the main ideas I want to show you in these two works. So I will two tales with dark photons. The first tale is based in this archive paper that we produced in January and is already published in JCAP, together with Bastian Diaz from Catholic University and Georg Jäckel from the University of Heidelberg in Germany. And the first tale is about this dark axion portal. Okay, so what is this dark axion portal? Well, dark axion portal puts together axions and dark photons, which are both popular beyond standard model candidates. And it's a compelling idea to consider them both belonging to this hidden sector, and one of them acting as a messenger. So if we want to construct a theory that includes both axions and dark photons, we can think about what possibilities do we have for couplings between them. And in principle, there are many couplings that we should consider, right? In particular, the couplings that are like this one I'm showing you, because the axion has this remaining shift symmetry. The axions only couple via derivative terms. And therefore, possibility to couple axions with photons is through this Chern-Simons kind of interaction. And also dark photons can mix or couple to photons, to visible photons, through the kinetic mixing. So in principle, you have a lot of terms that could relate axions, dark photons with photons. But if we claim that there is some set 2 symmetry in the hidden sector, we find that this pure dark axion portal emerges because this set 2 symmetry will impose that this axion field, which is a pseudo-scalar, transforms as minus the field, the same for the dark photon U1, and the standard model is not charged under this set 2 symmetry. And therefore, when you look at the possible couplings that now you can construct by imposing this symmetry, you find that this one I wrote here, which is a coupling between the axion, the standard model photons, and the dark photons, is the only coupling surviving. And therefore, this is quite nice, because we find a way of isolating the, if you want, like the dominant term in the sense that when you impose this set 2 symmetry, is actually the only term that it is possible that couples axions to dark photons. If one of them is the dark matter candidate, you see that in order for this dark matter candidate to communicate with the standard model via photons, is through the other dark particle. Interactions only happen, as I said, when the other dark state is present. Usually, axions and dark photons are considered lightweight. And in that sense, they can be really long-lived because they are lightweight, and therefore they are kind of naturally protected from decaying. But when they are not lightweight, this Z2 symmetry protects the lighter dark state from decaying. So it is also quite natural to think that in the case they are not lightweight, this Z2 symmetry it's needed in order to make them stable. Since the interaction between these dark particles is non-renormalizable, it's an operator 5, dimension 5, the freezing is in the UV kind. And therefore, we will see that there is always a population produced at the highest temperature in the universe. So this means that you want it or not, if you assume a model that has axions and dark photons, which is, let's say, protected by this Z2 symmetry, this freezing production mechanism always happens. And it happens at the highest temperature of the universe. And in that sense, we always find this population produced via UV freezing. So now I will put in a more concrete terms the model I want to present you. So in here I have the kinetic term for the dark photon together with a mass. And this mass can be generated in different ways via a dark Higgs mechanism or via a Stuckelberg mechanism. In here we have the axion and a mass for the axion, thinking therefore that there is some new U1 symmetry that is spontaneously and explicitly broken such that we have a mass for this particle. And we have this interaction term between them that I call LF or LB. So LF, I already introduced you, is this coupling, what I call this dark axion portal, where the axion and the dark photon are coupled to the visible photon. But above the electroweak scale, we should change this F mu nu by the hypercharge. And this is what we do, even though I will always use the same name for the coupling, just as not to changing my notation, but in principle, keep in mind that if I motivate the production above the electroweak scale, I will be using the hypercharge. We will concentrate in a natural scenario when one of them is heavier than the other. In this work, we assume that the dark photon is the heavier particle, and the ALP, the axion-like particle, is the lighter one. We will assume they are above the mega electron volt scale, and this dark photon therefore is unstable and can decay into an axion and a photon, and therefore the ALP is totally stable and is the dark matter candidate. So the production mechanism, as I said, will be freeze-in. So we construct our Boltzmann equations, which are written in here. So we have a Boltzmann equation for the axion-like particle and for the dark photon. For the production processes that I will consider are these lepton, anti-lepton into the scalar and the dark photon. We also can have a production via the W plus and minus. And so these two production mechanisms are go with the coupling, with this G coupling squared. And we could also have photon annihilation into a pair of ALPs or a pair of dark photons, but these processes are much more suppressed than these others because these go with the coupling to the fourth. Okay, so we construct therefore our collision term in the regular way, and we can have, as I said, two different kind of regimes depending on the hierarchy between the masses of the particles and this reheating temperature. First, I assume that the reheating temperature, which I remind you for me is the highest temperature in the universe, it's above both masses of the dark particles, and therefore the relevant production mechanism is via this fermion annihilation into gamma prime and phi. And when you compute the yield of this dark photon and the ALP, you find they are the same. And as promised, this yield depends on this reheating temperature, as expected. And therefore, this production basically doesn't depend on the particle's mass. On the other case, this case 2 will be the strong coupling free scene. So if you assume that the reheating temperature is below either both dark states or at least one, in this case the mediator, the dark photon, and that the reheating temperature is much smaller than the electroweak scale. Again, you have that the main production mechanisms are via this fermion annihilation and the photon annihilation. I will not show you the yields because they are much more involved in terms of the parameters of the model, but I can show you this plot that maybe is more illustrative. That in this plot, we are seeing the coupling of the model of this dark axion portal versus the reheating temperature. So when the reheating temperature, and sorry, I have not said that in here, I have fixed masses for the dark particles. In particular, the mass of the dark matter is fixed, and the mass of the dark photon is 2 gigaelectron volts for this red curve, 10 gigaelectron volts for the yellow, and 30 for the black. So at first, for let's say reheating temperatures of the order of 10 gigaelectron volts, the production is basically given by this fermion annihilation. And as the temperature decreases, the reheating temperature decreases, this stronger free scene regime is start to trigger, and you see that the coupling needs to raise in order to accomplish for the total relic abundance of dark matter. So, by the way, all the lines here fulfill the correct relic abundance. All the points in the lines fulfill this correct relic abundance. And as I keep decreasing the reheating temperature, let me focus on this black curve just for as an example. Eventually, the process of fermion annihilation doesn't have enough energy to produce the dark photon, because in this case it's 30 GeV. And we reach this threshold where this process doesn't happen anymore. But the production then is taken via the photon annihilation. If you remind, I showed you that 2 photons can give a pair of ALPs, axion-like particles. So therefore, we don't need to produce the dark photon in this case. And this is what we see here. But for this process to dominate, I remind you that that process goes as decoupling to the 4th. So that's why decoupling needs to increase a lot in order to give the correct relic abundance. And this is typically the behavior we expect for these 2 particles in the early universe. Because when we produce these particles at the reheating temperature, we have a population of axion-like particles and a population of dark photons. But eventually, the dark photon will decay into a photon and an axion with this rate. And we will end up with 2 populations of axions. One that is coming from the reheating, and the other that is coming from the decay of this dark photon. And therefore, 2 scenarios can happen. First, that the dark photon from the reheating is already non-relativistic when the dark photon decays, which would be this scenario. So in here, I'm showing you energy densities as a function of the scale factor. This is the radiation energy density in terms of the scale factor. The energy density is multiplied by the scale factor to the 4th, and that's why you see that the radiation density is horizontal, except for changes in the degrees of freedom. And the dark photon is, since it's the heavier, it's non-relativistic, and therefore its energy density redshifts as the scale factor to the -3, and eventually decays. And decays into photons and axion-like particles, so gives its energy to photons and axion-like particles. And that's why you see this bump here in radiation. And you also see a bump here for the energy density of axion-like particles. And in this case, the axion-like particles are non-relativistic at the moment of the decay of the dark photon, but this relativistic population appears. But this relativistic population dominates the energy density, because it goes as the temperature Q. And eventually, this population also becomes non-relativistic, and it continues redshifting as matter. The other possibility is that the axion-like particles is relativistic at the moment of the dark photon decay. So you see in here, the dark photon is decaying around this time. We have the population of axion-like particles, which are relativistic. And they join this new population coming from the decay, which is also relativistic. And it stays relativistic much longer in this case, until eventually it becomes non-relativistic in this around this scale factor here, and then it redshifts as matter. Of course, we need that the dark matter, in this case the axion-like particle, redshifts or behaves as matter before matter radiation equality in order for this to be a viable dark matter model. And this brings me to what are the cosmological constraints for the model. So we want that Big Bang nucleosynthesis is successfully carried on, the same with the CMB. And therefore, we should be sure that the decay of this dark photon doesn't interfere with the success of Big Bang nucleosynthesis by injecting photons into the plasma and changing the baryon to photon plasma, the effective number of neutrinos, and so on. And in order to account for these cosmological constraints, we will be using the results of this paper that they basically took into consideration. And here I have, this is the papers, limits on non-relativistic matter during Big Bang nucleosynthesis. Basically, they consider these two scenarios. So if eventually before Big Bang nucleosynthesis, but kind of around Big Bang nucleosynthesis, you have something that behaves as matter and decays electromagnetically and invisibly, in the sense that it decays to some dark particle. What are the constraints from Big Bang nucleosynthesis and CMB? In principle, we have strong constraints from photodisintegration of this light nuclei that says that the lifetime of this new matter, let's say whatever it is, in the case of this paper, for us will be the dark photon, should the lifetime should be smaller than 10 to the 4 seconds, which translates in energy that the decay should happen before the temperature in the universe is of the order of the kilo electron volt. And they parameterize the ratio of energy densities of this new matter field to the radiation in the universe at the moment before Big Bang nucleosynthesis, so around 10 mega electron volts. And as you can see, what they constrain is the value of this ratio of energies as a function of the lifetime of this new matter particle. And you find that in principle, this psi parameter should be smaller than around 10 to the minus 5 if you impose that the lifetime is smaller than 10 to the 4 seconds, in order not to interfere with Big Bang nucleosynthesis and CMB. Okay, so this is what we will also require in our model. We will steal these results and apply them to our model. And we will also require that the dark matter velocity has to be smaller than 10 to the minus 2 times the speed of light in order not to interfere with the structure formation, because otherwise the dark matter has too much kinetic energy and the free streaming length is too long, and it can the matter cannot form these potential wells needed for accretion of matter and formation of structures. So these are our cosmological constraints that we apply to our model to find the relevant parameter space for dark matter production. So in the case 1, where we have this standard free scene, so the reheating temperature above the dark matter, both dark matter and the dark photon mass, we see that for high reheating temperature, so in here I have the coupling versus the dark matter mass for different reheating temperatures. So if we are in a scenario of high reheating temperature, so around 10 to the 14 GeV, we find that the model, it's only compatible with the dark matter paradigm for quite heavy dark matter masses. So these are much above the giga-electron volt. So this red line here. But as you allow the reheating temperature to decrease, you find that the parameter space starts to enlarge, and that smaller masses for the dark matter are possible, till reaching almost the kilo-electron volt range. Yeah, and in the second case, this free scene at strong coupling. So when you have that the reheating temperature is slightly below the dark matter mass and the dark photon mass, the parameter space is much more restricted. In here we have plots for different reheating temperatures, so 5 MeV, 100 MeV, and 1 GeV for the coupling versus the dark matter mass. And you see that in the case of quite low, almost in the border of the allowed reheating temperature of 5 MeV, we have that the coupling, it's indeed larger than what I showed you before, and for a small range of dark matter masses. As you increase the reheating temperature, then the parameter space enlarges a bit more, but also I would say not that much. And we have detection opportunities because from direct detection, we can take already constraints for this coupling that have been taken from B factories, beam dumps, and colliders. By considering that this dark photon, since it's long-lived, it can act as a long-lived particle and decay into a photon and an ALP. And this has been constrained in different experiments that you see here. So in principle, the color area, the blue and the orange, corresponds to two different reheating temperatures where the model is allowed. And the lines here show the parameter space that can be ruled out by these searches. Only the ones that are in this solid color are the ones that have been performed, and the other are expected constraints. So as you can see, the model can be quite can be constrained, even though we have two particles in the hidden sector, and therefore this is quite a quite nice opportunity to already use bounds from experiments to constrain this kind of models. And in what it in the rest of my talk, I will tell you briefly about this second chapter, where we consider two kinds of portal. A kind of dark axion portal together with a Higgs portal, and this is based in this archive number in collaboration again with Bastian Diaz, Lucia Duarte, Joel Jones, Walter Rodriguez, and Danilo Segar. So in this case, we considered a pseudo-scalar, which before it was our axion-like particle, but in here I will not call it axion-like particle because I don't respect the shift symmetry anymore. So you can call it axion still, but let's say you need to find a way to motivate this strong violation of this U1 symmetry. And this pseudo-scalar has a portal term with the Higgs, and also has a portal with the photons via dark photons. So the same coupling I showed you before. In here, we are interested in the case where the scalar is lighter than the Higgs, particularly lighter than half the mass of the Higgs, that the reheating temperature is below the mass of the scalar, and the lighter state is the dark photon that will be our dark matter candidate. In principle, the processes that we are interested in keeping track of is this fermion annihilation, but this fermion annihilation can happen now also mediated by the Higgs particle into these two scalars, or as I showed you before, via the photon or the set boson into the scalar and the dark photon. And we also expect that the scalar will decay into photon and the dark photon. So the production mechanism I will consider is also freeze-in. So this is an example of the possibilities we have. And now we have two kinds of portal. And this is important because it totally changes the phenomenology of the model. So for instance, when you have no Higgs portal, so when you turn off the Higgs portal, you find what I showed you before, this UV freeze-in. But as you increase the size of this Higgs portal, you start to see that this infrared freeze-in also plays a role. And in particular, if you choose a quite high value for the Higgs portal, like this 0.1, which is the solid line, you find that the scalar can actually thermalize in the early universe. Then it does freeze out and eventually decays into the dark photon. For the other cases, 10 to the -3, the scalar does not thermalize and also freezes in. If you now increase the strength of the dark photon portal now, you find that the decay of the scalar is faster, happens at a higher temperature, and this can actually prevent the scalar for freezing out. As you can see here, for instance, let's look at this coupling of 0.1. So again, the scalar thermalizes, follows the thermal, the equilibrium distribution. But now it doesn't freeze out because the decays prevent it for doing so, and instead leaves thermal or chemical, in this sense, equilibrium. And the dark photon, the same as before, freezes in always, and is highly influenced by the decays of the scalar particle. These are more or less how can we understand the behavior of these production mechanisms. So when you have low reheating temperatures, the dominant production is for the dark matter is via this UV contribution, because basically G is allowed to increase a lot to compensate for the dark matter relic abundance, and that's why you see here this kind of behavior. But as you increase the reheating temperature, this infrared freezing can be more important, and can compete in production with this other channel, and eventually can dominate the production. Okay, and this is what we see in this vertical line here, where the production doesn't depend on this GD anymore, but actually depends on lambda, on the parameter of the Higgs portal. And then in here you can see the differences between the two masses. And this is just a complementary plot showing the same, but now in terms of the coupling of the Higgs portal with the reheating temperature, where basically it tells you that for smaller values of this coupling, the production is dominated by this UV freeze-in. But in here, when the hidden portal, the Higgs portal is seizable enough, you can have this freeze-out production. So the dark matter changes not the dark matter, sorry, the scalar particle changes the production mechanism, and it becomes independent on this lambda particle, lambda value. And in here we also have detection opportunities, because now, in principle, well, again, you will have that this now scalar field is a long-lived particle that will decay into the dark photon. But now this scalar particle can be produced by the Higgs. So you can search for this process in Atlas by the decay of the Higgs to the two scalars, and then each scalar decays into a photon and a dark photon, basically with this decay length. And therefore you can have three possibilities of searching for signatures of this model, basically displaced photon signatures, Higgs-2 invisible, and Higgs-2 undetected. So what we did is that we did a recast of the Atlas results for displaced photon searches by simulating the decay of the Higgs particle into these events. This is the sensitivity of Atlas to our model via, so in here we have for two different masses of the mediator of the scalar particle, 30 GeV, the blue curve, and 60 GeV, the orange one. And the most sensitive way of, the most sensitive is the displaced photon search, as you can see here, in the case of 60 GeV or 30 GeV. Then we have the Higgs-2 undetected, which is this limit here, the flat colored regions. And this is the limit from Higgs-2 invisible. We identified a golden window based on the couplings that are accessible to the Atlas results, and the couplings to the Higgs portal and to the dark photon portal. We identify this golden window where we would like to search for masses of the scalar between around 20 GeV to 60 GeV with this range of dark photon couplings. This basically will give us the decay length that we need in order for these searches to be sensitive. We also need quite efficient decay of the Higgs into these scalars, and that's why we look for this range of the Higgs portal parameter. And we need that the mass of the dark matter, in this case the dark photon, is not that high in order for the transverse photons to have enough energy, and therefore we restrict ourselves to masses below 1 gigaelectron-volt. And since we want the reheating temperature to be around this value, we focus on reheating temperatures of the order of 3 GeV. This is the parameter space where this model can account for the viable dark matter candidate and the dark photon. We applied all cosmological constraints I also showed you before for the other work that also apply here. And what you are seeing here is the dark photon coupling versus the scalar mass, and the bands here are masses or reflect the masses of the dark photon between 1 and 5 GeV, 1 and 5 GeV. And the values between these lines correspond to values of the Higgs portal in powers of 10 to the minus 4. So for instance, in here, this, let's say this part that is allowed, we can have a dark matter candidate between 1 and 5 GeV with a mediator of masses of the order of between 25 and 30 GeV, and the range of Higgs portal values is 0.1 times 10 to the minus 4, so 10 to the minus 5 in order to properly account for the dark matter. And G is, of course, in this range. And everything that is shaded in gray is not viable as a dark matter parameter space. And everything in white can be filled by values between these ranges of the Higgs portal parameter. So in principle, we have a lot of parameter space where this model can account for the dark matter. You see that there are bands that overlap. So for instance, in this region here that overlaps with this one, we can also have a dark matter between 1 and 5 GeV for, let's say, a scalar mass of the order of 30 or 20-something GeV, but with a Higgs portal of 1,000 times 10 to the minus 4, meaning 0.1. So the reason you can find dark matter for 10 to the minus 5 in lambda and 10 to the minus 1 is because we have these two regimes where the scalar thermalizes in the early universe and freezes out and then decays out of equilibrium, or this would be this parameter space here, or the case where it never thermalizes and freezes in, which is this parameter space here. Now, if we confront this with the sensitivity from the LHC constraints, so in here, I show you the parameter space kind of similar, the coupling to the dark photons, the mediator mass. This has been done for dark photon mass of 1 GeV, and the scale of colors is in times of lambda to the minus 3. So this is the maximum allowed lambda in order not to interfere with the data from LHC. And when you confront with the parameter space from the model, you find that in the case of the non-thermal scalar mediator scenario, you can rule out all this parameter space. Let's say the parameter space where the mediator is above around 45 gigaelectron volts for this kind of couplings. So these are my results, and this brings me to my summary. So we ruled out the possibility of a thermal scalar, meaning a strongly scalar coupled to the Higgs particle. Therefore, this last scenario can only happen via the non-thermal mediator scenario. So this is still a viable scenario for a dark matter mass of the order of 1 GeV. And we foresee that if we lower, let's say, the dark matter mass, this would be totally possible from the experimental, let's say, the experimental bounds, and for the cosmological viability, because lowering the dark matter mass can be accounted by also lowering the reheating temperature or lowering the mediator mass. Most likely there will be stronger constraints from cosmology, but certainly we expect that some parameter space still remains available. And my general summary is that freezing at low reheating temperatures is an attractive scenario to have a non-thermal dark matter production with moderate to strong couplings such that they can be searched for in experiments. And despite allowing these two particles in the hidden sector, the models I have presented to you offer quite rich phenomenology from the cosmological point of view, and they are also quite testable in current and future experiments. Yeah, that's it. Thank you very much.
Thank you very much, Paola, for the very nice and very complete seminar. Question from the audience? Alfonso, please.
Hi, Paola. Thank you very much for this very nice talk. And let me ask a very, very, very basic question. So please excuse me for asking a so basic question. In your Lagrangians, you always use the phi coupling to the strength tensor and to the dual strength tensor. Yes. I know that the motivation is because initially you want to work with actions, but I suppose that you are not interested anymore in solving with this kind of action the strong CP problem. No. But why you don't allow also the coupling of the scalar to the strength tensor and another strength tensor, with not the dual, but the original one?
Okay, yeah. This is totally possible. It's just that I'm always working with the pseudo-scalar. And if you have the pseudo-scalar, then you need the dual and not the, in order for this to be invariant, let's say. I don't want
but that is a physical motivation to work with pseudo-scalar and not the scalars for the dark matter model?
I would say that you are right, that this comes from that I like axions in principle, that strong CP problem and so on, and therefore they are pseudo-scalars. Because they have this connection with the strong CP problem. That's why I consider, but it would be, I would expect quite similar results if you abandon this idea and you say this is a scalar, and therefore you just couple to F and not F dual, let's say. This would be totally analog. I would not expect different results at all.
Okay, thank you.
Tesio, please. Tesio, you're muted. You had a question, Tesio. We don't hear you, Tesio.
Well, I was trying to unmute. Can you hear me now?
Yes, we can hear you.
Yeah, okay. So first, thank you very much, Paola. Very nice talk. Very interesting subject. I found very interesting this scenario of freezing at low reheating temperature, because always when I hear about freezing, you see the couplings and they are 10 to the minus 10, 10 to the minus 15, I don't know, ridiculously small. And having freezing at higher couplings is very interesting, I found. So one question is, one thing that is very important in these scenarios is the reheating temperature. It plays a very important role. So what determines the reheating temperature? You need to come up with a full inflationary model to predict the reheating temperature, and what should happen in order for this temperature to be that small for the of MEV, GeV.
Yeah, this is a really good question. I mean, the details of the inflationary period are quite unknown in that sense. So what you would need, in principle, I mean, usually we assume what is called instantaneous reheating, meaning that you have your inflaton that decays into standard model particles quite instantaneously, really abruptly. And if it's like that, and this happens at a really high scale, then most likely you will end up with this high scale inflation. But you could have that the reheating period extends in the sense that it's not instantaneous anymore, and the inflaton itself has a lifetime. And therefore the inflaton could dominate the energy density of the universe as a matter field, okay? And eventually decay, not instantaneously, at some lower temperature. So this would be a scenario where you would, and this of course, this extended reheating scenarios are quite ubiquitous in inflationary models, and therefore this would be a motivation to think that the decay of the inflaton doesn't need to be fast once, but that the inflaton can have this lifetime, and therefore decay at a much smaller temperature as long as doesn't interfere into Big Bang nucleosynthesis period.
So, but you need what they call an early matter-dominated era. Is that what you're saying? Because in this case, it doesn't have to be the inflaton itself. It could be another field that dominates the energy content of the universe, and you have this matter-dominated evolution and so on.
I see your point. Well, this is also another possibility. So let's say the inflaton actually decayed at a high temperature. But then what I'm saying would not work. So I really need low temperature reheating in that sense, because I showed that these particles are produced from the primordial bath at the highest temperature of the universe, which I'm assuming is the reheating temperature, but also doesn't need to. I didn't want to go into that details, but doesn't need to be actually the reheating temperature, the highest temperature attained in the universe. But as long as you have standard model particles at some temperature, they will produce this population of dark sector particles at the highest temperature. And this will happen. So even if, let's say, I have that the inflationary period happened at a really high scale, these particles will be produced there. And then you can have an early matter domination by some other field that is not the inflaton from cosmic inflation, but some other matter field or whatever. But these particles, these dark sector particles I motivated here will be already produced at the highest temperature. So,
and if there is another period of matter domination, they will be produced again, or not? I mean, the production will happen every time you have this kind of physics of reheating, as I'm understanding.
Meaning the production happens all the time. The only thing is that the dominant production happens at the highest temperature. And therefore, if you have a matter-dominated era after that, the only thing that it could influence is the decay of the of my mediator, because the decay could happen in a. I assume that the decay happens in a radiation-dominated era, and if it's not the case, the physics changes. But this I think would be the only change I could have. So in principle, that's why when I'm saying low temperature reheating, I'm saying about really the reheating that produces the primordial bath of particles.
The thermal bath. I see. Okay. I have another questions. Other questions. So a follow-up question of this by Alfonso regarding this coupling between the axion and dark photon. I'm wondering if this coupling violates parity.
No, you mean the coupling of the scalar, pseudo-scalar with the photons and the dark photons?
Dark photons, yes. Because in this case, I don't know, but maybe you could search for these particles or set constraints from experiments, from parity violation experiments, such as.
No, but there is no parity violation because
there is no.
This term is, this FF dual is E dot B, right? Electric field dot magnetic field. So under parity, you have that the electric field changes, but the magnetic field doesn't, because it's a pseudo vector. So, and you have a pseudo-scalar that also transforms under parity, and therefore the coupling is even under parity transformations.
Okay. So in this case, forget. And a final question, if I may.
Yeah, sure.
Yeah. A curiosity, in that slide that you showed the bounds from beam dumps, low energy accelerators, and so on. So there is this proposal of a beam dump experiment in Brazil using the Sirius facility. I was curious about whether this proposed accelerator could have any sensitivity to this kind of new physics.
You are right. I haven't checked there. It's electron positron.
Yeah, it's a positron beam. Yeah.
Yes, you are right. I should have considered. Yeah, I don't know the sensitivity, because in principle I think there. Let me think. They are more sensitive to the fermion coupling, if I remember correctly, than the photon coupling. So I'm not sure if they would reach the parameter space that I'm showing, but I should check. Yeah, I should check, because you are right. I haven't, in principle, checked this. Hopefully they do. Yeah.
Okay. Thank you, Paola. Thank you.
Yeah, thank you.
Any more questions? Any more questions from the audience? Paola, I had a question. You were showing in some of your plot the allowed range for the dark matter mass for different value for the reheating temperature. And for lower value for the reheating temperature, lowering the value was giving an increase there before. I seen the plot before there and the plot before.
This one?
Yes, this one. Yes. Can you please provide us some comment why we had this larger range when lowering this value for this reheating temperature?
Okay. Yeah, I mean, because the freezing in this scenario, you remember it's a UV freezing, so it depends directly in this reheating temperature. When you have a high reheating temperature, most likely you will overproduce the dark matter. And that's why only for this, you need to go to really small couplings in order for this scenario to be viable. And that's why only this parameter space remains, because it's the one with the lowest coupling. So basically, to answer your question, is because you reduce the dark matter. But as you allow the reheating temperature to decrease, the yield of the dark matter decreases, and this allows you to go into higher couplings, and this raises the mass of the dark matter, such that in here for this standard freezing scenario, the smallest temperature of reheating I took is 1 GeV, and in here this small value allows you to reach couplings of the order of 10 to the minus 10 GeV to the minus 1, and therefore this also allows you to have smaller dark matter masses because of the relic abundance and the dependence on the mass and G, because the yield depends on G squared and the relic abundance depends on the mass. Because it doesn't depend on the mass.
Thanks a lot, Paola. I had another question. How you consider also the scenario, for example, of this dark photon to be lighter than this Axion pseudo-scalar? You were considering the case of this axion to be lighter than the dark photon. Now, what about the other scenario?
I mean, the other hierarchy scenario is completely viable. It was just a matter of choice in both works, actually, to consider. In the first one, we consider the dark photon as the heavier dark particle, and the ALP as the lightest, and in the other work, the opposite. But this is a matter of choice. Also, the results should be basically the same by choosing the other hierarchy. The only thing, of course, is that, I mean, for the last work I presented to you, we need this coupling with the Higgs, and we need that the one that couples to the Higgs is the long-lived particle. So in this scenario, we need that the axion-like particle or the scalar is the heavier, and the dark matter, that is the dark photon, the lighter one, because we want that the one that couples to the Higgs is the long-lived particle. So in this model, the hierarchy is more clear why it has to be like that. But in the first one, it was just a matter of choice.
I see. Also, I see in the other scenario for this axion to be lighter than the dark photon, it may also, yes, there will be also the constraint from the direct detection. There will be also this constraint from direct detection from this Lux experiment.
Yeah.
So in principle, it will be an extra constraint in the other scenario.
In the other scenario, yeah.
Question from the audience? Any more questions? If there are no more questions, we thank Paola for the very nice and very excellent seminar. Thank you so much, Paola, for the excellent, for your very nice and very complete seminar. Thank you so much. And we meet at the next seminar.
Bye.
Bye. Bye.
Bye-bye.
Bye-bye. Thank you so much. Bye. y apago acá la grabación.
¿Tienes que parar la grabación?
Sí, detener.
Y después